Hey everyone, and welcome to this explainer. If you're tuning in today, you're probably the kind of person who likes to cut through the noise and get straight to the actual mechanics of how things work. So we're going to take a calm, structured look at the foundational principles of electrical engineering. We're leaning directly on university-level materials and some really cool, authentic, handwritten engineering notes to guide us. Whether you're an engineering student who needs a solid refresher, or honestly just a curious mind trying to decode the invisible forces that literally power our modern lives, just settle in. We're going to break this all down, logically, step by step. Let's start things off with a pretty simple question. What actually happens when you flip a light switch or, plug your phone into the wall? I mean, it feels totally instantaneous, almost like magic, right? But just beneath that everyday action is this beautifully orchestrated flow of microscopic particles, and they're all governed by some incredibly strict universal rules. So today, we're mapping out that unseen world. We'll strip away all the overwhelming complexity and just look at the bare anatomy of a circuit to understand exactly how we harness this energy. All right, here's our roadmap for today. We're going to build this up progressively through 4 quick parts. Number 1, the foundation. Number 2, powering the system. 3, meet the network elements. And finally, number 4, the rules of the circuit. Let's jump in. Part 1, the foundation. Particles and forces. Let's zoom way in and start at the absolute smallest scale imaginable. Okay, so it all really begins with charge. Charge is just a characteristic property of subatomic particles. Protons carry a positive charge, electrons carry negative charge. It's a fundamental property of matter, honestly, very much like mass. In the electrical world, we measure this charge in a unit called coulombs. You can kind of think of charge as the primary currency of electricity, because without it, absolutely nothing happens. Now, just take a second to look at the sheer scale here, or, well, the lack of it. This tiny number, negative 1.6 times 10 to the negative 19th power, that is the exact charge of a single solitary electron in coulombs. It is an unfathomably small number. To put that into perspective, it brilliantly illustrates that one single electron, it doesn't really do much on its own. It literally takes billions upon billions of these microscopic particles, all moving together to do anything useful, like, say, lighting up the screen you are watching this on right now. And at mass movement, that brings us right to our next definition, electric current, which we represent with the letter I. Current is simply the rate of flow of that electric charge over time. The math here is easy. I equals Q divided by T, so charge divided by time. We measure this in amperes or amps. If you picture charge as individual water droplets, then current is the rushing river. It's the physical motion of those billions of electrons traveling down a wire. But as we know, a river doesn't flow without gravity, and electrons definitely don't move without a push. That's where EMF comes in, electromotive force, and potential. This is the actual physical force that causes the current of electricity to flow. We commonly measure this potential difference in volts. So the crucial thing to remember here is this. Voltage is the push, and current is the resulting flow of the charge. They are super intimately connected, but they are entirely distinct concepts. All right, part 2, powering the system, work in energy. Now that we've got our pushing force and our flowing particles sorted out, let's look at the macro-level output. This brings us to a pair of concepts that are incredibly easy to mix up, but seeing them side by side makes the distinction pretty obvious. Electrical power, which is measured in watts, is the rate at which work is being done. You calculate it by multiplying voltage and current, so P equals V times I. Electrical energy, on the flip side, is measured in joules, and it's the stored capacity to do work over time. So energy equals power multiplied by time. To keep it super simple, power is how fast you're getting the job done right now, while energy is the total amount of work you actually manage to accomplish over the entire day. And we can actually see this math in action here, straight out of the foundational textbook. Just look at these waveforms. Graph A up top shows our current, and graph B shows the voltage. Now notice what happens in graph C, which represents power. When both voltage and current are present and actively doing their thing, the power curve spikes right upward. It's a great visual proof that power is the direct product of voltage and current interacting at the exact same time. Honestly, seeing the math represented as visual waves really kind of anchors the whole concept, doesn't it? Moving right along to part 3, meet the network elements, the players. Because these invisible forces, they need physical roads to travel on. So let's meet the components that direct traffic. In circuit design, we like to organize network elements into highly logical buckets. First up, we've got active versus passive elements. Active elements, think of a battery or voltage source, they actually supply energy to the circuit. Passive elements, like resistors or capacitors, they don't supply energy at all, they just absorb or dissipate it. We also categorize them as linear versus nonlinear. A linear element behaves predictably in a straight line, completely satisfying Ohm's law. But a nonlinear element, like a diode, it changes its behavior depending on the conditions. Filing components into these clear-cut categories just dramatically reduces your cognitive load when you're staring down a really complex schematic. Check out this authentic handwritten study note. I absolutely love seeing this kind of raw, structured thinking. It essentially maps out the entire family tree of network elements. You can see the split right at the top. Active elements on the left, so your voltage and current sources, and then the passive elements on the right, which are your resistors, inductors, and capacitors. It's just a beautifully simple hierarchy that takes what could be a really overwhelming list of electrical parts and turns it into a digestible, organized system. And that brings us to part 4, the rules of the circuit, bringing it together. We've got our fundamental forces. We've got our physical components. Now, we just need the universal laws that dictate how they all actually interact. Let's kick this off with the most famous rule of the bunch, Ohm's law. It states that at a constant temperature, the current passing through a conductor is directly proportional to the voltage across it. The formula is legendary. V equals IR. Voltage equals current multiplied by resistance. This is really the ultimate bridge. It mathematically connects the pushing force, the flowing charge, and the physical component that's resisting that flow. If you only walk away remembering one single equation today, definitely make it this one. Now, beyond Ohm's law, we also need to know how current behaves when it hits an intersection. This is Kirchhoff's current law, commonly called KCL. And I promise it is way simpler than the name suggests. It's basically just 3 low-pressure steps. First, you identify a node, which is just a junction where a few wires meet up. Second, you add up all the currents entering that node. And third, you ensure the algebraic sum equals 0. What does that mean in plain English? Basically, whatever current flows into a junction, that exact same amount has to flow out. No charge magically goes missing, no charge just magically appears out of thin air. It's just pure logical accounting. What's really fascinating here is seeing KCL placed right side by side with its sibling, KVL, Kirchhoff's voltage law. Over on the left, from the handwritten notes, you see the KCL point rule. If you track the arrows, currents I1 and I5 are heading in, while I2, I3, and I4 are heading out. They balance out perfectly. Then on the right, we've got the KVL loop rule, which applies a very similar logic but to voltage around a closed circuit loop. The total voltage supplied, minus the voltage drops across the resistors, it will always equal 0. When you put them together, the point rule for current and the loop rule for voltage basically give you total mastery over analyzing any basic circuit out there. So, here is the big, crucial takeaway I want you to have from all of this. Engineering is not about magic. It's really just about scaling logic. Every single complex piece of electronics you interact with today, whether we're talking about the smartphone in your pocket, the laptop on your desk, or a massive supercomputer, they are fundamentally operating on these exact same rules. They are literally just scaling up Ohm's law, tracking current through KCL nodes, and balancing voltage in KVL loops across billions of tiny microscopic pathways. When you master these basics, you are quite literally holding the blueprint for all of modern electrical engineering. Which leaves us with a pretty peaceful, yet, provocative thought to close out on. We've journeyed all the way from the unfathomably tiny scale of a single electron's charge, right up to the universal rules that govern entire global power grids. If these incredibly simple rules, just a push, a flow, an intersection, and a loop, if they can scale infinitely to create the technology that defines our whole modern world, what complex system could you build simply by mapping out your own nodes and loops? Thank you so much for learning with me today on this explainer. Keep analyzing, keep asking questions, and I'll see you in the next one.